Until now, we have seen many publications claiming that Einstein was wrong at the quantum level. The topic became such an obsession for humanity that proving Einstein's mistake about quantum entanglement was considered worthy of a Nobel Prize. But a very recent study suggests that general relativity holds true even at the quantum scale. We have never been this close to a theory of everything. An experimental study that brings general relativity and quantum mechanics together has been published in a prestigious peer-reviewed journal. This discovery has caused such excitement in the scientific community that we could not stay indifferent and made this video right after the paper was released. Quantum mechanics and general relativity are two highly successful theories that describe different scales of the universe. But these two theories do not work in each other's domains. Large celestial bodies and subatomic particles do not follow the same rules. This has always seemed strange to me because large objects are simply made up of smaller ones. How is it possible that the fundamental laws governing them are completely different? This is exactly why we do not yet have a single theory of everything that unifies them. But that may be about to change. A new paper published by physicists from Gila at the University of Colorado, the Max Planck Institute in Germany, Harvard University, and the U.S. National Institute of Standards and Technology gives us an important clue. According to the paper, understanding the interaction between quantum mechanics and general relativity is one of the biggest challenges in modern physics. Until now, no direct experiment have been able to test both theories at the same time. But with advancements in atomic clock measurement technology, an interaction that was once thought impossible can now be observed. In this study, scientists examined how quantum mechanics and general relativity could be unified by analyzing the quantum states of atoms alongside the effects of gravitational time dilation. Time slows down near the center of the Earth and speeds up as you move away from gravitational fields. This is one of the key predictions of Einstein's general relativity and has been tested countless times at the macroscopic scale, always proving to be correct. The slowing of time near a black hole and the aging difference between an astronaut near a black hole and an observer far away, just like what happened to Cooper in Interstellar, are all consequences of this effect. However, until now, it was unclear how gravitational differences affected time at the atomic scale. Scientists had never been able to test whether time flowed differently at the quantum level. If time dilation existed at the atomic scale, it would be extremely small, less than 1/trillionth of a second. The paper confirms that this effect is measurable at around 1 second divided by 10 superscript 1 superscript 2, or 1 picosecond. While this may seem irrelevant to everyday life at the atomic level, this time shift is highly significant. This is where advances in atomic clock technology become crucial. Thanks to optical lattice clocks, which provide an extreme level of precision, such tiny time differences can now be detected. These clocks are 100 times more precise than traditional cesium atomic clocks and are sensitive enough to measure how physical events in the universe affect time. NASA and the European Space Agency are planning to use these clocks in space to detect gravitational waves and study dark matter. This experiment was made possible using the most advanced optical lattice clock technology available. If you are wondering what optical lattice clocks are, they're the most precise time-keeping devices ever built. These clocks measure time by analyzing the oscillation frequencies of atoms trapped in an optical lattice created by laser beams. By stabilizing atoms with lasers and keeping them at absolute temperature levels, these clocks allow for measurements far more precise than standard atomic clocks. Without such a clock, finding the bridge between the quantum world and the macroscopic world would be impossible. If gravity slows down time at the atomic level, this means that general relativity also applies at the quantum scale, which could be one of the most groundbreaking discoveries since Einstein. That is why, as soon as this paper was published, just 4 days ago, we decided to make this video. How was this experiment conducted? Scientists placed atoms inside an optical lattice, a structure created with laser beams to hold them in place. This method essentially traps the atoms, stabilizing their positions and significantly increasing the accuracy of time measurements. What does it mean to trap an atom with laser beams? Simply put, an atom naturally oscillates at a specific energy level. If a laser beam is applied in the opposite direction of this oscillation and sustained continuously, the atom reaches its lowest energy state and its movement is significantly restricted, almost like being tied with an invisible string. During this process, the atom absorbs photons from the laser beam, loses energy, and its oscillations decrease. In the experiment, strontium atoms were placed inside the optical lattice and functioned as highly precise clocks. These atoms allowed scientists to measure the effects of gravitational time dilation at an unprecedented scale. Inside an optical lattice, the position of atoms is determined by the energy levels set by the laser's power and frequency. Higher energy lasers trap atoms in the upper regions of the lattice, while lower energy lasers keep them closer to the bottom. If general relativity applies at the quantum level, atoms positioned higher should experience a faster flow of time, while those lower down should experience a slower one. This effect can be tested by precisely tuning the laser-generated energy levels. For example, the oscillation frequency of atoms held at a specific height should differ, although by an extremely small amount, from those positioned lower. This frequency shift provides the fundamental data needed to confirm gravitational time dilation at the atomic scale. According to the paper, the height difference measured in this experiment was only 1 millimeter. That means scientists have successfully measured time dilation at the atomic scale due to a mere 1 millimeter difference in altitude. This is truly an astonishing achievement. Imagine we have two atoms with a height difference of just 1 millimeter if both experience time at the same rate, or if the atom position higher experiences a slower time flow. General relativity would not hold at the quantum scale. However, if the higher atom experiences time moving faster, then this confirms that general relativity remains valid even at the quantum level. Now, let's dive into the details of this groundbreaking experiment and witness every step of a discovery that could redefine our understanding of physics. Time is measured based on the principle that atoms transition between energy levels at specific frequencies. But what does this mean? Atoms emit electromagnetic waves at precise frequencies, and these oscillations create the most stable natural time-keeping mechanism. In fact, the definition of 1 second is based on atomic vibrations. For example, a cesium-133 atom oscillates exactly 429 trillion times as it moves between specific energy states. When this number of oscillations is completed, 1 second has officially passed. Our entire time-keeping system relies on these atomic oscillations. In this experiment, instead of cesium-133, strontium-87 atoms were used because they are better suited for measurements with optical lattice clocks. The oscillation frequency of strontium-87 is extremely high. If a strontium-87 atom oscillates exactly 429 trillion times, this corresponds to 1 second in human perception of time. The experiment examined whether atomic oscillation frequencies changed at different heights. If the atom positioned higher oscillated faster, meaning it had a higher frequency, this would confirm that general relativity holds true even at the quantum scale. The measurements were conducted with extreme precision. Think of it as comparing the timekeeping speed of a clock on the first floor of a skyscraper versus one on the 50th floor. In the experiment, atoms placed just 1 millimeter higher oscillated more than those positioned lower. As predicted by general relativity, time slows down in regions with stronger gravity, causing the atoms lower in the optical lattice to oscillate less than those higher up. Strontium atoms normally oscillate about 429 trillion times per second, but atoms positioned just 1 millimeter higher had a slightly increased frequency, meaning they oscillated slightly more. Meanwhile, atoms positioned lower oscillated slightly less due to gravitational time dilation. This direct measurement of time dilation at the quantum scale represents an incredible breakthrough in physics. At the atomic level, time is measured by tracking the oscillation frequencies of atoms. This measurement is done using ultra-precise atomic clocks, specifically optical lattice clocks. Now, let's break down how this process works step by step. These measurements